Welcome to this scientific lecture on capillarity and surface tension as the powerful engines driving microfluidic motion. At the microscale, surface tension dominates over gravity, creating fascinating phenomena that enable advanced microfluidic technologies. Let's begin by understanding surface tension at the molecular level. Molecules in the bulk liquid experience equal forces in all directions, but surface molecules have unbalanced forces, creating tension. Surface tension gamma is the energy required to create new surface area, measured in joules per square meter or equivalently newtons per meter. Gamma equals energy per area, which is equivalent to force per length. For water at 25 degrees Celsius, gamma equals 72 millinewtons per meter. For typical oils, gamma is approximately 30 millinewtons per meter. When interfaces curve, they generate remarkable pressure differences across the surface. Think of liquids as pulling themselves like stretched elastic membranes, and curved surfaces create pressure jumps. A curved interface generates pressure pointing toward the center of curvature. This is the Laplace pressure. The Laplace pressure equals gamma times the sum of inverse radii of curvature in two perpendicular directions. For a sphere, both radii equal r, so the pressure difference simplifies to 2 gamma over r. Let's calculate actual pressures in microscale structures to see how powerful capillary effects become. How much pressure can a curved meniscus generate in a 10 micrometer pore? Let's calculate this explicitly. The radius is 10 micrometers, which equals 10 times 10 to the minus 6 meters. Surface tension of water is 72 times 10 to the minus 3 newtons per meter. Laplace pressure equals 2 times 72 times 10 to the minus 3 divided by 10 times 10 to the minus 6. This equals 14,400 pascals, or about 14 kilopascals. That's approximately 0.14 atmospheres, a significant pressure from such a tiny interface. Now let's see what happens in a larger 100 micrometer pore. The pressure drops to 1440 pascals, 10 times smaller because the radius is 10 times larger. This inverse relationship is crucial. Smaller radii generate dramatically larger pressures. The capillary number tells us whether surface tension or viscous forces dominate fluid motion. The capillary number equals viscosity times velocity divided by surface tension. When Ca is much less than 1, surface tension dominates. When Ca is much greater than 1, viscous forces dominate. At Ca near 1, they compete. Let's calculate typical capillary numbers for water in microfluidic systems. Water viscosity is 10 to the minus 3 pascal seconds. Typical velocity is 1 millimeter per second, or 10 to the minus 3 meters per second. Capillary number equals 1.4 times 10 to the minus 5, much less than 1, so surface tension dominates. Surface tension can spontaneously pull liquids into narrow channels without any external pump. When a liquid contacts a narrow hydrophilic channel, it spontaneously fills the channel due to capillary action. The contact angle between liquid and solid determines whether capillary filling occurs. If theta is less than 90 degrees, the liquid wets the surface and fills the channel. If theta is greater than 90 degrees, the liquid does not wet the surface and filling is blocked. The Washburn equation describes how fast a liquid fills a capillary tube. The filling length L grows as the square root of time, proportional to surface tension and contact angle, inversely proportional to viscosity. Capillary forces control droplet formation in microfluidic devices, creating monodisperse emulsions. In flow-focusing devices, a dispersed phase breaks into uniform droplets, surrounded by a continuous phase. Droplet formation occurs when the balance between Laplace pressure and viscous stress reaches a critical point. Breakup occurs when the capillary number is comparable to the ratio of channel width to emerging droplet length. Typical microfluidic droplets range from 10 to 200 micrometers in diameter, with excellent uniformity. Passive capillary pumps use surface tension gradients to move fluids without external power. A capillary pump uses a porous absorption pad at the end of a channel to continuously draw liquid through the system. The flow rate depends on channel cross-section, length, and the capillary pressure at the meniscus. Flow rate Q equals pi r to the fourth times pressure difference, divided by 8 times viscosity times length. Let's calculate flow rate for a 50 micrometer channel, that is 1 centimeter long. Pressure is about 3,000 pascals, radius is 25 micrometers. Flow rate is approximately 0.4 nanoliters per second, perfect for diagnostic assays. Paper microfluidics harnesses capillary action in cellulose fibers for ultra-low-cost diagnostics. Paper-based devices use hydrophobic barriers to create channels where samples flow by capillary action to detection zones. Paper microfluidics offers incredible advantages for point-of-care testing. No external pumps are needed, devices cost pennies to make, and they are fully disposable. Cellulose fibers create pores ranging from 10 to 50 micrometers, ideal for capillary flow. Typical flow speeds are 1 to 5 millimeters per minute, sufficient for rapid diagnostics. Modern diagnostic chips use capillary networks to automatically route samples without user intervention. Self-filling chips use designed capillary networks to split samples, perform reactions, and deliver to multiple test zones simultaneously. The key design principle is controlling the filling sequence through engineered resistances and capillary pressures. Filling timescales as length squared times viscosity, divided by surface tension, radius, and cosine of contact angle. Some devices even separate blood cells from plasma, using capillary action in specially designed membrane structures. Let's calculate how high water can rise in a capillary tube, a classic demonstration of surface tension power. In a narrow tube, water rises to height h, where capillary pressure balances gravitational pressure. Laplace pressure 2 gamma cosine theta over r equals density times g times h. Solving for h gives 2 gamma cosine theta over density times g times r. For water in a 100 micrometer tube, let's calculate the rise height. H equals 2 times 0.07, 2 times 1, divided by 1,000 times 9.8 times 50 times 10 to the minus 6. This gives approximately 29 centimeters of rise, a dramatic effect in such a thin tube. In a 10 micrometer tube, the rise height would be 2.9 meters, though other effects would limit this in practice. The ratio of surface tension forces to gravity determines when capillary effects dominate. The bond number equals density times g times L squared, divided by surface tension. When bond number is much less than 1, surface tension dominates over gravity. When bond number is much greater than 1, gravity dominates over surface tension. For water at length scale 100 micrometers, let's calculate the bond number. Bond number equals approximately 1.4 times 10 to the minus 4, much less than 1, so surface tension dominates. Different liquids behave quite differently in microchannels due to their surface tension and viscosity properties. Water has higher surface tension, but much lower viscosity compared to typical oils, leading to different microfluidic behavior. For a 50 micrometer channel with 1 millimeter per second velocity, let's compare capillary numbers. Capillary number for water is 1.4 times 10 to the minus 5. Capillary number for oil is 1.7 times 10 to the minus 3, about 100 times larger due to higher viscosity. Oil flows more slowly due to higher viscosity, but maintains more stable interfaces with less tendency to form droplets. Capillary valves use geometry changes to control when and where liquids can flow without moving parts. A sudden expansion creates a capillary valve where liquid stops until sufficient pressure builds up to overcome the larger radius. The burst pressure equals 2 gamma divided by the large radius, the minimum pressure needed to pass the valve. The valve opens automatically when upstream pressure from filling exceeds the burst pressure threshold. The capillary number precisely determines droplet size and production rate in microfluidic systems. As capillary number increases, droplets become larger because viscous forces begin to resist the pinch-off more effectively. Droplet diameter scales with channel width times capillary number to the power 0.3. For precise droplet size control, we adjust flow rates of both phases to tune the capillary number. Let's design a real diagnostic chip and calculate its performance parameters. Consider a 5 mm long channel, connecting a sample reservoir to a detection zone. Channel dimensions are 50 micrometers wide, 30 micrometers deep, and 5 mm long. The hydraulic radius is approximately 20 micrometers. Capillary pressure is 2 times 0.072 divided by 20 times 10 to the minus 6, giving 7,200 pascals. Flow rate equals pi times 20 micrometers to the fourth times 7,200 divided by 8 times 10 to the minus 3 times 5 millimeters. This gives approximately 1.8 nanoliters per second. Time to fill the entire channel is about 4 seconds, ideal for rapid point-of-care testing. Let's summarize the key principles governing capillarity and microfluidic motion. Laplace pressure, scaling as 2 gamma over r, drives spontaneous capillary flows in microchannels. Smaller structures generate dramatically larger capillary pressures, making microscale ideal for surface tension dominance. The capillary number determines whether surface tension or viscous forces control the flow behavior. These principles enable passive pumps, paper diagnostics, and precise droplet generation without external power. Effective microfluidic design requires carefully balancing capillary pressures, hydraulic resistances, and geometric features. These two equations, Laplace pressure and capillary number, are the fundamental engines of microfluidic motion, enabling remarkable technologies at the microscale.